All right, hello all. My name is Alex Averla. My partner is Ariel Yui, and we will be presenting an algorithm on parallel fast tetrahedral meshing. So tetrahedral meshing is the problem where you're given an input mesh, which is a bunch of triangles which tile a surface, and then these enclose a volume, and you want to create a tet mesh which tiles the interior volume as well as the surface. There was an algorithm presented for this at SIGGRAPH 2020, which improved upon previous algorithms. And the idea is you're given this triangle mesh, and then you do some simplifications on it, combining close vertices. Then you generate this background mesh you see at the bottom. And once that's done, you iteratively add in triangles in the triangle soup that was given to you so that the background mesh better reflects the surface generated by the triangle mesh. And you continue doing this until you've inserted all triangles. And that's the idea. And it kind of cuts the interior volume out of this background mesh. So the key part of this algorithm we're parallelizing is the sequential triangle insertion. When you insert a triangle, you have to compute the tets which are intersecting it in the background mesh and then subdivide those tets in order to get a finer background partition. This is a local operation, which also turns out to be non-local because of data structures, and it's what we'll be discussing.
Our approach for triangle insertion starts by partitioning the background mesh into different sections that can be operated on safely in parallel. Then we have to localize the vertices that are used in the triangles into the different sections of the partition. And once we've localized the vertices, we can then localize the triangles to figure out which section of the partition they're in. Then we do the parallel insertion over these localized triangles. And finally, we sequentially insert the triangles that were unable to be inserted in parallel. We tried two different partitioning schemes. So with uniform partitioning, we split the space into equally sized uniform boxes. And with uniform partitioning, we can easily compute which box each triangle is in, but it doesn't do as well on workload balance. And for octree partitioning, we get a better workload balance, but it creates more overhead. So with an octree, we can recursively split the space so that the triangles are distributed more evenly. We implemented this on the 40-core Andrew Unix machines using shared memory parallelism. We used these machines because we wanted to test on various core counts up to 32. The original code is written in C++ and uses thread building blocks, or TBB. TBB has a number of higher level parallel constructs, such as dynamic scheduling. So we mainly used the dynamic scheduling in order to operate on parallel for loops. We also used scoped mutex locks when modifying shared data structures.
So our results. Each of these graphs you see here represents a single mesh, which you can see visualized at the top, and then over different processor counts and partition schemes. And the general theme we see going on here is that it's actually quite difficult to achieve the time given by the baseline for a number of reasons. Partitioning turns out to be very hard because some meshes are pathological, and we have these large clumps of triangles which clump up, and so we don't see much speed up over time because they create a bottleneck in the parallel computation. However, this isn't always the case, and for meshes that behave reasonably well, we do get sub-baseline speed and speed up. So for example, if you look at this Yoda execution time, we get good speed up there.
The main impediments to parallelism we had were that the mesh data structure was difficult to work with in parallel due to the way that the triangles are stored. We had to put locks around large sections of the code, which resulted in essentially sequentializing parts of the code that could be theoretically done in parallel. Additionally, we had a balance between the workload balance and the amount of sequential work. As we partition the space more finely, then we get a better workload balance, but it increases the amount of triangles that are on the border between multiple parts of the partition, which have to be inserted sequentially. So in this diagram at the bottom, we can see that parallel time decreases, but sequential time increases. This concludes our presentation on the parallel fast tetrahedral meshing algorithm.